What if I told you there's a planet that should not exist? Not because it's far away, not because it's hard to see, but because every rule of planetary science says it should be impossible. Imagine a world orbiting a dead star, the collapsed core of a sun that exploded in a supernova, a star so dense, so violent, that it tears atoms apart with radiation, a place where planets are supposed to be erased from existence. And yet, something is still there. This planet doesn't move in a gentle, yearly orbit. It screams around its star in just a few hours. The gravity is so extreme that the planet isn't even round anymore. It's stretched, distorted, pulled into a shape that looks more like a lemon than a world. Its skies may be filled with carbon soot, not clouds. Deep beneath its surface, scientists think diamonds could be forming under crushing pressure. No oceans, no blue sky, no familiar air. This isn't science fiction. This isn't a theory. This is a real object, detected by NASA's most powerful telescope. And here's the part that shocked astronomers the most. NASA wasn't even looking for something like this, because once you understand where this planet lives, everything you know about planets starts breaking down. Why this discovery blew up the internet? When the headlines first appeared, they sounded almost too extreme to be true. Phrases like "planet that defies all logic" and "impossible world discovered by NASA" spread rapidly across news sites, social media feeds, and science forums. For many people, it felt like just another exaggerated space headline designed to grab clicks rather than convey real science. That skepticism was understandable, because astronomy headlines often stretch language far beyond what the data actually shows. In recent years, the phrase "defies logic" has been used so often that it has almost lost its meaning. Worlds that are simply hot, cold, large, or small are routinely described as unbelievable, even though they still fit neatly within existing models of planetary physics. Most of the time, once you look past the dramatic wording, the discoveries make sense when explained properly. That is why many scientists and space enthusiasts initially approach this story with caution rather than excitement. But this time was different. As more details emerged, it became clear that the reaction wasn't driven by hype alone. The observations came from the James Webb Space Telescope, the most powerful space observatory ever built, designed specifically to analyze distant worlds in ways that were impossible before. Webb doesn't just take pictures, it breaks starlight into chemical fingerprints, revealing what planets are made of and how they behave under extreme conditions. As astronomers began sharing what Webb had detected, the tone of the conversation changed. This wasn't just an odd planet with a strange orbit or unusual temperature. The data hinted at something far more challenging to explain, something that didn't comfortably fit into existing categories of planets. Scientists were cautious with their words, but the implications were clear. This object was forcing a serious re-examination of long-held assumptions. And yet, even with all this attention, the strangest part isn't the planet itself. It's where it exists, and what that location tells us about how violent, unpredictable, and creative the universe can be. We haven't even said its name yet, but understanding its environment is where everything truly starts to unravel. What we thought planets were. For most of modern astronomy, planets followed a fairly simple and reassuring story. They form from giant clouds of gas and dust that collapse around a newborn star. Over millions of years, tiny particles collide, stick together, and grow into larger bodies. Eventually, gravity takes over, shaping these growing worlds as they clear paths in their orbits. This process, called planetary accretion, explains everything from rocky planets like Earth to gas giants like Jupiter, and it has worked remarkably well for explaining what we see in our own solar system. One of the strongest rules to come out of this understanding is shape. Planets are round because gravity pulls matter evenly toward their center. Once an object becomes large enough, gravity overwhelms the strength of rock and metal, forcing the body into a sphere. That is why Earth, Mars, Jupiter, and even distant Neptune all share the same basic geometry, despite their differences. Deviations exist, but they are tiny. Even fast-spinning planets only bulge slightly at the equator, never enough to truly change their overall form. Atmospheres follow similarly predictable patterns. Rocky planets near their stars tend to have atmospheres made of nitrogen, oxygen, carbon dioxide, or traces of water vapor. Gas giants collect enormous envelopes of hydrogen and helium. These compositions make sense when you consider temperature, gravity, and distance from the star. Earth's atmosphere supports life, while Jupiter's thick hydrogen clouds reflect its massive size and deep gravity well. Across thousands of observed exoplanets, these trends repeat again and again. Over time, these observations hardened into rules. Planets form in disks around stars. They become spherical under gravity, they settle into stable orbits, and their atmospheres reflect both their mass and their environment. Even the strangest worlds discovered over the last few decades still fit somewhere within this framework. They might stretch the limits, but they do not shatter the foundation. At least, that was the assumption guiding planetary science for generations. And then, astronomers found a planet that breaks almost every one of these rules. A world whose location, shape, and composition refuse to behave the way planets are supposed to, forcing scientists to confront the possibility that our neat definitions were never as complete as we believed. The dead star. To understand why this discovery is so unsettling, you first have to understand what happens when a massive star dies. Stars far larger than our Sun burn through their nuclear fuel at an incredible rate. When that fuel runs out, gravity suddenly wins. The core collapses in a fraction of a second, triggering one of the most violent events in the universe, a supernova explosion. For a brief moment, a single star can outshine an entire galaxy, blasting its outer layers into space and releasing unimaginable amounts of energy. What remains after that explosion is not a normal star at all. The core collapses so completely that protons and electrons are crushed together, forming neutrons. The result is a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. These objects are typically only about 20 kilometers across, roughly the size of a large city, yet they contain more mass than the Sun itself. Gravity here is no longer familiar, it is extreme, beyond everyday intuition. Some neutron stars become something even more dangerous. As they spin, often hundreds of times per second, they emit focused beams of radiation from their magnetic poles. These beams sweep across space like a cosmic lighthouse. When one of these spinning neutron stars is aligned just right with Earth, we observe it as a pulsar. Pulsars are among the most precise natural clocks known, but they are also deadly. Their radiation is powerful enough to strip atmospheres, disrupt matter, and sterilize anything unfortunate enough to be too close. This is why pulsars are considered some of the most hostile environments imaginable. The original supernova would have violently cleared out nearby space, destroying or ejecting any pre-existing planets. Afterward, the intense radiation and gravitational tides of the pulsar should prevent new planets from forming or surviving. For decades, astronomers assumed pulsars were essentially planetary graveyards, places where worlds go to die, not places where they could exist. To visualize it, imagine space being constantly swept clean by invisible blades of radiation, rotating again and again with mechanical precision. Anything nearby is bombarded, stretched, and eroded over time. In theory, no stable planet should be able to hold itself together in such a region, especially not one with an atmosphere or complex structure. According to everything scientists understood, this environment should be empty, yet somehow, something is still orbiting it. Against expectations shaped by decades of astrophysics, a planetary object has managed to survive in the shadow of a stellar corpse, circling a pulsar where planets are not supposed to exist at all. The planet that shouldn't exist. The object at the center of this story finally has a name, and it sounds as cold and technical as the environment it inhabits: PSR J2322 2650b. There is nothing dramatic about the name itself, but what it represents has stunned astronomers. This is a planetary mass object confirmed to be orbiting a pulsar, the dense remnant of a star that exploded long ago. Just that single fact already places it among the rarest types of planets ever detected. While Earth takes 365 days to orbit the Sun, and even Mercury needs 88 days to complete a single year, this planet races around its pulsar in just over 7 hours. In less time than it takes to sleep through the night, the planet completes an entire orbit. That speed alone hints at how close it must be to its host, and how extreme the gravitational forces acting on it truly are. The distance between PSR and its pulsar is so small that it feels almost impossible. Mercury, the closest planet to the Sun, still sits tens of millions of kilometers away from its star. This pulsar planet orbits far closer relative to its host, deep inside a region flooded with radiation and intense tidal forces. At that distance, even a slight instability should tear a planet apart, yet this one remains locked in place, orbit after orbit. Planets around pulsars are not just unusual, they are extraordinarily rare. Out of thousands of confirmed exoplanets, only a handful are known to orbit pulsars at all. Most were discovered decades ago and remain difficult to explain. Each new example challenges the assumption that supernova explosions erase the possibility of planetary systems. PSR J2322 265b stands out even among these oddities because of its tight orbit and unusual physical properties. What makes this planet emotionally striking is not just its strangeness, but its history. For PSR J2322 265b to exist at all, it had to endure the violent death of its parent star. It either survived a supernova blast that should have destroyed it, or it formed afterward from the wreckage left behind. In either case, this is a world that lived through a cosmic apocalypse and remained intact, circling the stellar corpse that once annihilated its surroundings. But surviving isn't the strangest part. Once scientists began looking closer at what this planet is actually like, its shape, composition, and behavior started raising even deeper questions, ones that survival alone cannot answer. A planet that isn't round. For as long as humans have observed planets, one feature has remained almost universal. They are round. The reason is simple. Gravity pulls material inward from every direction, and once an object becomes large enough, that pull smooths out mountains, valleys, and irregular shapes. Rock flows, metal bends, and gas settles, all working together to create a sphere. This is why Earth, Mars, Jupiter, and even distant exoplanets share the same basic shape despite enormous differences in size and composition. The force that threatens this rule is something called tidal gravity. Tidal forces occur when gravity pulls more strongly on one side of an object than the other. On Earth, the Moon's tidal pull gently stretches our planet, raising ocean tides and causing a barely measurable bulge. Even with Earth's rotation added in, the planet is only about 0.3% wider at the equator than from pole to pole. Under normal conditions, gravity easily keeps planets close to spherical. PSR J232265b exists under conditions that are anything but normal. Orbiting extremely close to a pulsar, it experiences tidal forces millions of times stronger than those Earth feels from the Moon. The gravity of the neutron star pulls so intensely that the planet is physically stretched along the line facing its host. Instead of relaxing into a sphere, the planet is forced into an elongated shape, often compared to a lemon or an American football. This is not artistic exaggeration. It is a real physical distortion driven by relentless gravity. This stretching pushes the planet dangerously close to what astronomers call the Roche limit. This is the distance at which a planet's own gravity can no longer hold it together against the tidal pull of the object it orbits. Cross that invisible boundary, and the planet would begin to break apart, its material pulled into streams or rings. So, what does it mean that a planet like PSR J2322 265b exists? At first glance, it seems impossible. A world orbiting a pulsar distorted into a lemon shape, with an atmosphere dominated by carbon chains and helium instead of oxygen or water. By all accounts, it shouldn't be there, and yet it is, quietly circling a dead star that should have destroyed everything nearby. Its very existence challenges everything we thought we knew about planets, atmospheres, and survival under extreme conditions. This is why scientists are captivated. PSR J232265b doesn't just break rules, it forces us to confront the limits of our understanding. It survives in the shadow of a cosmic apocalypse, endures tidal forces that should rip it apart, and carries an atmosphere unlike anything we have seen before. Every measurement, every observation pushes us to ask new questions, to expand our theories, and to reconsider what is truly possible in the universe. And yet, for all the data, all the telescopes, and all the calculations, we still do not have all the answers. 99.7% confidence. When headlines blasted the phrase 99.7% chance of life, they were referring to something very different from what it sounds like. Scientists didn't calculate a 99.7% probability that alien life exists on K2-18b. What they measured was the strength of the signal, the likelihood that the spectral fingerprint JWST detected isn't just random noise in the data. In statistics, this kind of measurement is called a 3 sigma detection. Imagine flipping a coin. If it's fair, you expect half heads and half tails. But if you flip it 1,000 times and get 600 heads, you'd start thinking something strange is happening. Now imagine you flip it 1,000,000 times and the pattern holds. That's closer to what sigma refers to, how unlikely a result would be if nothing unusual were really happening. A 3 sigma result means that if the atmosphere of K2-18b had none of these intriguing molecules, the odds of getting a false signal this strong from sheer randomness would be about 0.3%. In other words, the data is unlikely to be a mistake, but that doesn't tell us what the signal truly represents. The universe loves to surprise us with chemistry we don't yet understand. In astrophysics and particle physics, the bar for declaring a discovery is higher, much higher. The problem begins when scientific language meets public headlines. Media outlets often treat sigma levels as if they directly translate to probability of life, because 99.7% chance of a biosignature signal sounds almost the same as 99.7% chance of alien life. It's not. One measures statistical confidence in an atmospheric feature, the other makes a claim about biology, something far more complex, uncertain, and difficult to prove remotely. Scientists are careful for a reason. A molecule can be misidentified. An unknown atmospheric process could mimic a biological signature. Instrument calibration might distort faint signals. Or, in the most humbling possibility, alien planets may produce molecules through chemical pathways that don't exist on Earth, meaning our assumptions could be wrong. So the real meaning of the 99.7% confidence claim isn't that we've found life, it's that JWST has detected something in the atmosphere of K2-18b that almost certainly isn't random, something real, consistent, and strong enough to take seriously, and in the search for life beyond Earth, that alone is monumental. Why scientists aren't celebrating yet? Even with the tantalizing detection of potential biosignatures on K2-18b, scientists are careful to temper the excitement. The first reason is that unknown chemistry scenarios could mimic the signals of life. While dimethyl sulfide and its relative molecules are strongly associated with biology on Earth, there is no guarantee that alien planets follow the same rules. Exotic atmospheric reactions, unusual photochemistry under a red dwarf star, or previously unobserved geochemical processes could produce similar signals. Another concern is the possibility of instrument artifacts. The James Webb Space Telescope is the most powerful observatory humanity has ever built, but even it is not immune to calibration errors, sensor noise, or systematic uncertainties. Multiple instruments and independent observations are required to confirm that the signal truly originates from the planet's atmosphere and not from a glitch in the data. The planetary structure itself adds complications. K2-18b is a sub-Neptune, far larger than Earth, with a thick hydrogen-rich atmosphere and potentially extreme pressure at its ocean layers. These conditions make interpreting atmospheric chemistry far more complex. Signals that seem biological to us may be entirely consistent with high-pressure, high-temperature chemistry that has no counterpart on Earth. Scientists emphasize that we cannot simply assume the same rules of life or chemistry apply. Even the researchers themselves express cautious wonder. One senior astrophysicist described the detection as incredibly exciting, the strongest hint yet of life outside our solar system, but we must not get ahead of ourselves. Another added that, until we see the same molecules with more precision in different wavelengths and rule out non-biological sources, this remains a compelling mystery, not a confirmation. These caveats do not diminish the significance of the signal. They highlight the delicate balance in science between discovery and certainty. K2-18b has opened a door to one of the most profound questions in human history. Are we alone? But as the data shows, that door swings both ways, offering hope and mystery in equal measure. The thrill lies not in certainty, but in the pursuit and in the anticipation of what future observations might reveal. The better than Earth claim. Some headlines have gone further than science, dubbing K2-18b a planet better than Earth. The reasoning comes from several factors. Unlike many rocky exoplanets that sit too close or too far from their stars, K2-18b orbits in the temperate zone of its red dwarf host. Its atmosphere appears relatively stable, and models suggest it could harbor a global ocean beneath the thick hydrogen layer. For scientists looking for life, these conditions make K2-18b a compelling candidate. A stable source of energy, abundant water, and a protective atmosphere are all prerequisites for life as we understand it, and on paper, K2-18b ticks these boxes. Yet the reality is likely far more extreme than Earth. The planet's hydrogen-rich envelope creates an atmosphere that is vastly denser and heavier than ours. Surface or ocean pressures could be crushing, tens or even hundreds of times greater than what humans or terrestrial animals can tolerate. The red dwarf star provides much less visible light than the Sun, meaning the planet is bathed in dim, reddish illumination, which would drastically shape any potential photosynthesis-based life. The temperatures and chemistry in such an environment may be hostile for complex multicellular organisms, and high-energy stellar flares common to red dwarfs could periodically bombard the planet with radiation. The type of life that might exist on K2-18b, if any, would almost certainly be microbial or plankton-like. Tiny organisms thriving in an ocean beneath layers of hydrogen and methane, similar in scale to Earth's oceanic plankton, but adapted to alien chemistry. We are not talking about forests, animals, or intelligent civilizations. Life would be simpler, but potentially abundant and resilient, clinging to survival in ways we are only beginning to imagine. This contrast highlights a key challenge. Human expectations of habitability are inherently Earth-centric. We imagine planets better than Earth in terms of comfort, gravity, breathable air, or familiar ecosystems. K2-18b may be better for microbial life in ways we barely comprehend, but for humans or complex organisms, it is a harsh, alien world. The lesson is clear. When it comes to exoplanets, what counts as habitable, or even better, depends entirely on the lens through which we evaluate life. If life exists, what could it be like? If life exists on K2-18b, it would almost certainly be radically different from anything on Earth. Beneath its thick hydrogen-rich atmosphere, the planet may host a vast global ocean, perhaps hundreds of kilometers deep. In such an environment, life could exist as microbial communities floating freely in the water, forming ecosystems similar to Earth's plankton but adapted to alien chemistry. These organisms might survive on chemical gradients, extracting energy from interactions between water, minerals, and atmospheric compounds rather than sunlight. Unlike Earth, where photosynthesis dominates life's energy cycles, K2-18b orbits a dim red dwarf star that emits mostly infrared light. Any light-dependent organisms would need to harvest energy from wavelengths much weaker than the Sun's visible light, possibly developing entirely novel pigments or biochemical pathways. Some scientists speculate that life could rely on chemosynthesis, using chemicals like methane or hydrogen sulfide for energy processes found in Earth's deep-sea hydrothermal vent ecosystems, but taken to extreme scales under K2-18b's pressure and chemical conditions. The ocean itself could create layers of distinct ecosystems. Near the upper reaches, microbes might interact with traces of starlight, drifting in a hazy twilight. Far below, under crushing pressures, life could exist entirely in darkness, sustained by chemical reactions and the movement of fluids through the ocean floor. These organisms might form vast colonies, glowing faintly with bioluminescence to communicate or attract partners, producing chemical signatures that eventually rise into the atmosphere, the very molecules JWST may have detected. Imagine it as an alien, watery world of quiet motion and chemical symphonies. Life could be abundant, resilient, and persistent, yet invisible to the naked eye, existing in forms that challenge every assumption about what life looks like. For scientists, the detection of potential biosignatures on K2-18b is not just data, it is a tantalizing window into what might be a truly alien biosphere, operating under rules we can barely imagine, yet potentially echoing the same principles that made life thrive on Earth. Why this discovery hits different. Throughout human history, we have looked up at the stars and asked the same question: are we alone? The detection of potential biosignatures on K2-18b touches something deep within that age-old curiosity. It is more than a scientific puzzle. It is a mirror reflecting our desire to understand our place in the cosmos. For centuries, life beyond Earth has been the domain of speculation, philosophy, and imagination. Now, with the James Webb Space Telescope, we are approaching a moment where that speculation can be tested. People crave confirmation of life beyond our planet because it challenges the very core of human identity. If microbial ecosystems exist on K2-18b, it would suggest that life is not a unique accident, but a natural outcome of chemistry and physics, a pattern woven into the fabric of the universe. That realization changes how we view ourselves, transforming Earth from a solitary oasis into one of many potentially living worlds. The psychological impact is profound. Knowing that life might exist elsewhere can inspire awe, humility, and hope. It encourages us to see the universe not as a cold, empty void, but as a place capable of nurturing living systems. It reminds us that the search for life is not just a scientific endeavor, but a human journey, a story of curiosity, persistence, and wonder that stretches across generations. Ultimately, the discovery on K2-18b hits differently because it touches the universal longing to connect with the unknown. It whispers the possibility that we are part of a much larger, vibrant cosmos, and that somewhere in the quiet oceans of a distant world, life may be quietly thriving, waiting for us to find it. Are we looking at alien life? The evidence from K2-18b is compelling, but far from conclusive. James Webb's observations have revealed molecules like dimethyl sulfide that, on Earth, are almost exclusively produced by living organisms. The spectral signal is strong, with a 3 sigma confidence level, suggesting that what scientists are seeing is real and not a statistical fluke. Yet, it remains a hint, not proof. Unknown chemistry, extreme planetary conditions, and the limitations of our instruments leave room for alternative explanations. Scientists themselves are cautious. They describe this detection as the strongest hint yet of life beyond Earth, emphasizing that extraordinary claims require extraordinary evidence. Confirmation will require additional observations, independent verification, and careful analysis to rule out non-biological sources. Even with these caveats, the discovery is historic. K2-18b has become the most promising candidate in the search for extraterrestrial life, a distant world whispering possibilities about biology beyond our planet. While we cannot yet say life exists there, the tantalizing signals have opened a new chapter in humanity's quest to answer one of the oldest questions in history. Are we alone? If this discovery has you wondering what else might be out there, drop your thoughts in the comments. Do you think we're truly alone in the universe? Or could life be thriving on distant worlds like K2-18b right now? I want to hear your theories, no matter how wild or cautious. Make sure to hit subscribe and turn on notifications, because in our next video we'll explore another mind-bending exoplanet discovery that could reshape how we think about life in the cosmos. For now, remember this: the universe might be whispering secrets across the light years. The real question is, are we listening?